we've had the privilege to pick up an idea that's lain dormant somewhat. It's been, a lot of work was done in the past in Kleinwächter labs, and then for some time there was nobody really who could really pick up this work and take it on. And now we've had a lot of fun doing exactly that. So what I'm going to show you now in this talk, and then afterwards up in the workshop, and then also afterwards in the evening for those who really want to follow the whole process and follow us into the night, where we also do many of our measurements. It's a line of work that's at a totally different stage of development to what Jürgen is presenting with the sun pulse. The sun pulse is very far down the development track, and it's right there where it's really exciting. You can go out and pretty much say, I want to take one of these and buy it, and we're going to use it. This is not like that yet. This is definitely a research project. We've also got very exciting results, and we're also definitely looking at it and thinking, wow, I mean, we're going to build one of these really soon and we're going to use it, and so on. We're making a solar concentrator. That's a parabolic mirror, a section of a parabolic mirror. We're splitting it into 6 segments at the moment, something like a modular design. And what you see in the movie is one of these segments. I think at this point we're showing this segment as it happens. Maybe one day all these segments are the same, but right now these 2 segments are the same, these 2 segments are the same. So we've got 4 different segment types in here making one mirror with a total surface area, effective aperture, total aperture of 4.5 square meters. So catching 4.5 square meters of sunlight. Yeah, there's lots of ways we can think of optimizing a mirror surface. One can think of building big mirrors and small mirrors, lots of small round mirrors, assembling mirrors from segments and so on. We are working very much on a principle. How do you make a lightweight mirror segment that then you can scale it and optimize it for different places and different applications and so on? And the question is how to make a mirror that's got a good quality optical surface at a fair price, because obviously you can make astronomical optics at astronomical prices, we know that.
Sure.
And an astronomical mirror of this size would already be millions of euros, like a real telescope mirror. And you can make very poor quality mirrors with a small concentration ratio out of simple kitchen foil if you want a low concentration ratio. Somewhere in there, there's a lot of very interesting possibilities, and this is one. I mean, this is the principle of the membrane mirror as Jürgen always wanted it. This is the thing. Basically, to create an optical quality surface, we're taking a piece of shiny plastic and inflating it into a cushion. So just blowing it up, and boom, almost for free, you've got an optical quality surface. It's definitely not an imaging quality surface. This is not a telescope quality mirror. But as a solar concentrator, we're getting over a 500 times concentration of a single segment, which means all the light on this 1 square meter or so is coming into a spot like this, just by taking a piece of shiny plastic and inflating it.
You can see it very clearly here. Now if you look at the surface now, it has wrinkles and it will spread the light everywhere basically. And
plastic bag.
Once we inflate it, you see that suddenly you see clear reflections on it from
very even
smooth.
It's
the way of getting it smooth.
Yes,
Gives it
in
a curve.
an even way. That's important.
Here's a glass parabolic mirror. A reasonably good one. You can point this at the sun, and we focus the sunlight. If the sun is up there, we will get a focus sort of here or so. Yeah? Parabolic mirror. And if you want to use this during the day to create a focal spot, you will point it at the sun as it travels over the course of the day. And as long as you keep it tracked very accurately on the sun, you'll get a fantastic image of the sun at the focus. A parabola brings parallel light rays to a geometrically perfect focal spot. The sun is a very large distance away, and it's very large, so it's not actually a point source. It will create a micro sun here in the focus. The larger the mirror, the more of the sun's energy I will collect, and the better the quality of the mirror, the more finely I'll be able to focus it. And the shorter the focal length, the smaller the geometrical image will be, and the hotter the image of the sun will be. This has a certain focal length, like a lens, yeah? And if that focal length is quite large, then you'll get a relatively large image of the sun, and if that focal length is quite small, you'll get a relatively small image of the sun. So you can look at that as a geometric imaging system, and there's a certain angular divergence in the incoming radiation, and that'll translate to a certain geometric spot size at the focus. That, of course, there's a relationship between the focal length and the aperture, the F number, that determines how much of the available incoming energy you're going to be able to get into your spot. Maybe it's not so important for everybody, but it's key for those who want to really go into the optics. There's plenty of these parabolic mirrors around the world, and if you're using them for solar work, then you put a collector here that's going to do something useful with the energy. Maybe you've got your high temperature Stirling engine, or you're going to take the heat out and you're going to use it somewhere else, so you've got some kind of collector and some kind of heat transfer fluid or something, and you track it during the day, and you need quite a big system because what's hanging up here is quite big and it's right up in the air when you point it through the day, but it's good. The difference that we're doing here geometrically is we're using a portion of the parabola that's not on the axis here, but we're using imagine we're using this area of the parabola, for example, and we're moving it in such a way that this focus point, instead of being up in the air and moving during the day, is down on the ground and is fixed. So that means maybe this is my collector here, something like this, and the mirror is oriented north-south. As the world is turning around the north-south axis, the mirror is basically not turning, and so it's a bit hard to see here, and it's maybe not so important, the actual geometric details at this point, but there's a way of taking a certain section of this parabola and rotating it here, but the collector's always sitting on the ground and is receiving you can make a big, bulky, heavy, efficient, perfect detector, whatever you want. You've got no heat transfer fluid moving, you've just got right there directly the energy you want. So geometrically, that's the segment of the mirror that I'm showing you. That's when we take this phrase that we're saying we're building a precision membrane fixed focus mirror. That's the fixed focus part. We've got a fixed collector sitting on the ground collecting the energy because of the mirror geometry. That makes things a little bit more difficult because here I've got if I've got a geometry like this, I've got a circular mirror segment, and if I'm going to work with this, you can imagine that's a more complex geometrical shape. This perimeter is already not a circle, and the curvature in this axis and this axis is somewhat different. So we've added complexity, but we've simplified the application. Okay, so much on geometry. Now, similar geometry to what we see in the kitchen, with the mirror that's in the kitchen, also has the same origin, also came out of Klein-Wächter Labs. The exact implementation is somewhat different, but the principle is very, very similar. That the mirror is moving on the north-south axis and the focus point is fixed, in that case in the kitchen, so the cook can stand there. The cook has got their cooking pot, so it's not flying across the sky during the day, but it's sitting there in the kitchen comfortably, and the mirror is doing the work. So the principle for this kind of mirror is the same. This kind of mirror is not designed to be used in a kitchen, but it's designed to be used in a workshop or in I'd say in a factory, in an industrial application, but I like to think of as a relatively small scale community industrial application. There's no reason why it needs to be. It could be a larger scale, but it brings a certain power into community hands. And so also in those kind of situations, you want a comfortable working place you've got a kiln or a furnace or something, a metallurgy setup, or maybe you're working with glass or something, and it's great, that's fixed and the mirror's moving. You don't want to be hanging up there in the sky. So we take on this additional complexity of an asymmetric system because the advantages it brings to the user. The membrane parts I touched on in the movie, you can see basically we and many others also, by the way, are thinking of using membranes for mirrors because they're so lightweight, they're so low embodied energy. You get an optical surface relatively cheaply, almost for free. The other people who are thinking about using membrane mirrors are mainly people who want to build space telescopes. So it's quite nice also that we have, on the eco high-tech community scale, we're working on the same thing as basically, the others are advanced space laboratories. In principle, that's the inflated membrane now. We've got a frame here. Sun's here. And this membrane is a transparent membrane. They're both made of the same material. We're using ETFE, the fluoropolymer, the same one that's used in many of Jürgen's inventions. This one's transparent, and this one's got a thin aluminium layer on the front surface. So this is the focusing element. Simplified a little bit. The light's passing straight through here, through the top membrane, and it's being focused by the bottom. I've drawn an on-axis mirror now, but that's the principle. So we've got this, they're both 100 micron thick film, so it's really an incredibly tiny amount of material. And this one's got a few nanometers of aluminium. We need the transparency in this implementation, we need the transparent film to make it possible to inflate it. What you could do, of course, you could equally well design a system that had a box here, a rigid metal box, for example. Then you could put your reflective film on the top of the box, tie it on the sides, and instead of putting air pressure in here, positive pressure, you could put in reduced pressure in here. And so in the same way you'd get your curved optical surface by a pressure difference. Basically the same thing. This way you've got a metal box, and it needs to be quite strong because you've got low pressure inside. Not very low pressure, but slightly low pressure, and slightly low pressure over a large area and a large force. So you need quite a strong, heavy box. Then you've also got your optical surface there. It's out in the rain and the dust. They're very tough, these films, so you can also do it like this. This way is lighter weight, and this is the way we're concentrating on at the moment. These films have 95% transmission, so we're not losing much on this top film, and we're protecting our optical surface. Then you can just wash this off with a bit of water every time it gets dusty, or wipe it down. It's a very, very tough film material. It's all very nice. The thing is, to get a good optical surface on here, what you need to have is a very evenly tensioned membrane film. We try a little thought experiment. If you imagine that we've got our mirror that you've seen in the video clip, and if you imagine that in the middle the film was somewhat tighter than at the edges, then when you inflate it, instead of getting a single beautiful curved surface like this, you'd get something that would look a bit more like this. Anywhere that you've got uneven tension in the film, you get an uneven optical surface. And remember, when we're talking about optical surfaces, we're basically interested in of the order of magnitude of the wavelength of light. So we're not talking about normal mechanical engineering tolerances. We're talking about really tolerances and effects that are a little bit beyond our normal intuition. You know, we're not talking millimeters, we're talking microns, submicrons, fractions of microns. And in milliradians, so really tiny fractions of a degree. So the question is, the main question here is, how do you get and how do you maintain an even foil tension? And there we tried a lot. To know what it can do, I want to look at one, like why do we want a high concentration precise mirror? Why is precision good? Why is high concentration good? Why do this? I want to look at one, it's not really an application, but one way of using it, and that's the cavity receiver. So to look very briefly at cavity receiver and blackbody radiation. Okay, blackbody radiation, the amount of heat that's radiated through a certain aperture, A sigma T to the 4. T is the temperature in Kelvin, sigma is the Stefan-Boltzmann constant, A is the area. Notice in there, T to the power of 4. Okay? So if you want to work at high temperatures, and this mirror is designed to give high temperature process heat for people who want to work at high temperatures, maybe to say that. Why do this? You do high concentration to get to high temperatures. By high temperatures I mean at the moment around about 1,000 degrees. We've got this T to the 4, this T to the power of 4, so you're getting a lot of radiative losses. So if you're making something 1,000 degrees hot in this area, it's actually also kicking out a great deal of energy itself. Okay? So what we want to do is basically make a little hole, let's say an aperture. So take our mirror. We want to send the energy in there. We've got a high flux of energy coming through this aperture. There's our collection optics. This is the mirror, the membrane mirror that I showed you. This is an insulated wall. And here we're going to do something with the light that we've collected. So here we've got the very highest intensity that we have. Now here at the back, what do? Let's make a cavity. We're going to collect that light, that energy, and do something with it. We're going to take that energy away with some transfer fluid, maybe. Maybe we're going to store it in this block. Doesn't really matter too much what we're going to do in there. This is like a fascinating area for many other people. This is a fascinating area for me. Here's our meeting point. I want to make this as small as possible so that what happens on this side can be as efficient as possible. Because over there, this is the area in which radiation comes in from the sun, and the area in which radiation comes out from whatever you're doing on the other side. Okay? So the bigger the hole, the more energy you've got being lost from whatever's going on the inside. The smaller the hole, the more energy you've got staying in. And the size of that hole is governed by how tight we can make this focal spot coming in. So if you would put something here, you might get 1500 degrees C, and you could also have 1500 degrees C over this whole area, as long as you're not taking any energy out from our existing system. But you want to take energy out, right? That's the whole reason you've got it. So you're probably not going to run at 1500 degrees C, but maybe rather at 1000. Yeah, this is the curve that Jürgen was talking about, and because of this T to the 4 dependence, there's a certain point where you start to really lose your efficiency. And that depends on the concentration. Mm-hmm. And on the mirror that we're working on at the moment, on these kind of relatively simple results that we're getting, 1000 is about here or so. This area, it really is a few percent of the optical imaging limit. So you're so far away from these astronomical numbers, and because of this T to the 4 dependence, the work that you have to do to get up to 5,000 degrees is crazy compared to the work you need to do to be at 1,000 degrees. And at 1,000 degrees, plus minus a little bit, you can work under 1,000 degrees. So much stuff works under 1,000 degrees where you are up at super efficiency, even with such a simple system. And quite a lot works in this area of like between 1,000, 1,500, where even with such a simple system, you're probably still at 50% efficiency. And by the time you go over 1,500, you're up into ultra specialized materials, ultra specialized cost, and you're kind of into a different regime that we don't need to get into. Luckily, we can hang around in this, which is relatively comfortable and still extremely powerful, extremely applicable, extremely useful, and where we're burning a vast amount of fossil fuel to work in this temperature area of under 1,000. Nobody's really burning fossil fuel to get up to 5,000 degrees. It's like this whole array of process heat applications. Pyrolysis is in there, by the way. So the guys who've been funding our work for the last year, they've got a really nice project, which is a waste plastics to oil pyrolysis project in India, where there's so much waste plastic in India and elsewhere. And you take that waste plastic, you put it in a sealed tank, close the tank, no air comes in or out, heat it up to 500 degrees C or so, break all the polymerization bonds, and your plastic basically goes back into oil, gas, and to carbon. It's a little bit of a step into the future to say anybody with a very simple workshop can highly efficiently create process heat at over 1,000 degrees Celsius. So there'll be a lot of things that we still haven't really got our heads around that we can do with this. Yeah, it's a solar furnace, it's a solar reaction chamber. It's very useful to directly replace things that we're already doing, and we'll see what else we can do with it. I've been working on this probably for the last 5 years or so in Italy, and intensely for the last year together with Daniel. And we've reached a point where we've got these quite beautiful mirrors now. We've been funded for the last year, and we're looking now for more funding, more or less matching funds that takes us on for maybe it's the next year, us and also our cooperation partners. So what you see is a very nice single mirror segment.
Yeah, maybe I just show you how the air comes in here. It is on. I like it a lot to see this. And now it's touching the rods, so we would be inflating it inside here a little more, then it comes off the rods for sure. And yeah, I don't know, I just like it. You see also that in the welding, even though if the welding is not so exact and also the frame might not be very accurate, the even tension is applied even though you're not very exact. So with that method, we are very good in the limits of our production, basically.
This is how we measure our mirrors these days. It's taken a while in development. If this is a perfect parabolic mirror, then it should focus the light from an infinitely distant object onto a point. We are, in a sense, of running the mirror backwards. So we've got a light source here where we would normally put our collector if this was a solar concentrator, and we have a camera out there at infinity, 250 meters away on the top of the hill. And that's a video camera, and it's hooked up over the network. We've got a little modified wireless system there, so that's reaching wireless up the hill, and we're running, at the moment we're running very simple commercial software, but we have other ways of doing it. So what the camera sees up the hill, you see here on screen. So the camera is seeing an image in the mirror of this screen from 250 meters away. And if we have a perfect mirror, the camera is essentially at infinity, and it should see this little greenish yellow dot in the center of the archery target over the whole of the mirror. So if we've got a perfect mirror, that whole mirror should appear on screen here as green. From this we can say it's looking really good.
Yeah, overall it's good.
And then we can say why. What is this?
Right.
What is this red? Is it too strongly a mirror, or too weak a mirror? Is it off to the left? Is it off to the right? We can analyze this all offline.